Hello. So can you all hear me? Am I audible?
Yes, sir.
Okay, and slides are also visible to everyone.
Yes.
So in the last class we started discussing about the condensation. We said that there is two types of condensation is there. One is the film wise condensation and drop wise condensation. The major difference which we have talked about both is film wise condensation, usually a film of condensate forms over the surface. Okay, and since this film is forming, this film itself acts as a resistance for the heat transfer. But unlike this, if you look at the drop wise condensation, in the drop wise condensation, the entire surface is not wetted by the liquid, and therefore droplets are formed at different locations, isn't it? And since some of the area of the surface is still in direct contact with the vapor, usually the heat transfer coefficient is very high, almost 6 to 7 times higher than the film wise condensation. But in terms of the practical application, when we see practical application, the most commonly seen condensation is a film wise condensation, because there we are interested in fast condensation, and also surface modification, choice of surface modification is not always available in a practical application. And because of that, the most commonly seen condensation in a practical application is a film wise condensation. Okay, so this is what we have seen in the last class. Thereafter, we started looking at the uh, derivation of heat transfer coefficient for a film wise condensation. So we have assumed that there is a vertical surface is there, and this vertical surface which is having the temperature TW, this TW is lower than the temperature of the vapor, and because of that this vapor is condensing on the surface and eventually it is forming a film. So as we move from this leading edge here in a downward direction, this downward direction we have represented as a X, whereas a horizontal direction we have represented as a Y. As we move in a downward direction, eventually more and more vapor will be condensing on the surface, and therefore this film thickness is going to increase. Okay. So there are three types of forces acting here: shear force, which is acting upward direction; gravity and buoyancy are acting. Gravity is acting in a downward direction, whereas buoyancy is acting in a upward direction. Also, we have made some assumptions here. We said that the film is laminar and fully developed, and also there is a zero interfacial shear. So interfacial shear, when I am saying there is no shear between this outer film surface and the vapor, there is no shear. Okay, again we are assuming that the liquid properties in this film are constant, these are not varying. Okay, typically we take these liquid properties at the average temperature of average temperature between TV and TW. So TV plus TW divided by 2, that average temperature we calculate, and we take all the liquid properties at the average temperature. The other assumptions which we have used is vapor is saturated. So this vapor is saturated. So there is no sensible heat transfer between this vapor and uh, this particular film. Okay, so the temperature of this vapor and the temperature of this film liquid in this film is same. That's what we are assuming. Okay. So again, heat transfer through the condensate film occurs only by conduction. So here you can see at this surface the temperature is same as TV, and TV is same as saturation temperature, but there is a temperature gradient across this wall and this film. That is why the heat transfer is taking place. So the resistance offered in this case is primarily because of this film, liquid film, which is present in between this vapor and this cold liquid, cold solid surface. So between that there is a film, and this film we are assuming that the conduction resistance is present, only the conduction resistance present between this surface, solid surface, and this vapor. Okay. Again, in addition to that, we are assuming that the z direction, in a z direction, which is nothing but a perpendicular to the screen which you are seeing, in that perpendicular z direction, there is no variation. There is no variation. Okay. And so there is no wall effect. There is no variation. In addition to that, we are assuming that this width is unity. So this assumption of width of unity is primarily is what everything we are calculating per unit this particular width. That's what it means. Okay. All right. So now the first thing is to do a force balance. So we are assuming a shell or an element at a distance x from the leading edge here and distance y from the left hand side. So this is the element we are assuming, isn't it? So this element will have a thickness of dx and the thickness in the horizontal direction will be delta minus y, since the film thickness is delta. And since we are assuming that it is at the distance of y, this particular thickness will be delta minus y. Okay. So here shear stress multiplied by area. So shear stress is acting in a upward direction. So the area which is important is the cross sectional area. That cross sectional area will be what? Dx into dz, and that dz or z we are assuming as a 1 here. Okay. So that's why we have eliminated z here. Okay. So mu into du by dy, this is nothing but a shear stress multiplied by area. So that gives me a force, and that is equals to again the gravity force which is acting in a downward direction F2. So that is given as rho L into G into volume. So volume in this case will be delta minus y into dx will be the area into a z, and z is again 1. So that we have eliminated here. Minus buoyancy force is nothing but rho Vg del minus y dx, and again z is there. So that z term which is there in all three individual terms, these are the z is eliminated from both sides, left and right both. So after simplification, what we get is, after simplification, we can represent this equation as du will be given as rho L minus rho V by mu L into G del minus y. Okay, that is what we are going to have, and multiplied by dy. This dx and this dx will get cancelled out, and we can integrate this equation. So after integrating, what we get is the velocity u. Velocity u is obtained as rho L minus rho Vg divided by mu L. In the bracket, since this right hand side we will have g del minus y dy we will have after simplification. So integration of that will be what? Del y minus y square by 2. So that's what we are getting. Del y minus y square by 2 plus integration constant c. Again, in this particular equation, this integration constant c we have to evaluate. So we will apply a boundary condition. So boundary condition in this case is what? At y equals to 0, u is 0. So that's what we are assuming. No slip condition we are assuming. At y equals to 0 here, my velocity should be 0. So that's what we are assuming. So with this, what we are getting is c comes out to be 0. So my velocity profile at any x can be obtained using this equation. Okay. Now from this velocity profile, I wanted to calculate what will be the rate of condensation at a particular x. So how I can do that? Velocity multiplied by area will give me a volumetric flow rate, and volumetric flow rate, if I multiply to a density, it will give me a rate of condensation. So I am trying to find out the rate of condensation here. But since my velocity is varying across this y direction, here you can see this velocity v is varying across this y direction. Here it is 0. Here it is 0, isn't it? You can see u is varying with y. Isn't it? So clearly, in order to find out the rate of condensation, I need to do the integration over 0 to delta, isn't it? Because y is varying from 0 to delta. Do you all agree with me? Up to this we have seen, up to this velocity profile we have seen. So do you agree that if we wanted to find out the rate of condensation, what we have to do is we have to integrate u into area into rho L in the limit 0 to delta. Do you all agree? Does it make sense to everyone what I'm saying? So usually how we do it? Usually we calculate the velocity. Velocity multiplied by area will give me a volumetric flow rate. Volumetric flow rate multiplied by density will give me a mass flow rate, which is nothing but the rate of condensation, isn't it? So the only problem in this case is this u is not fixed. It is varying along the y direction. And therefore we need to integrate between 0 to delta, because y is varying between 0 to delta. Do you all agree in this equation what we are doing?
Yes, sir.
So this u, expression of u, we can put it here, isn't it? And again, integrate it between 0 to delta. So after integration, what we get is rho L minus rho v g del cube divided by 3 mu L. So this gives me the mass flow rate or a rate of condensation at any x. Remember, this delta here is a function of x. So this delta I am actually referring to what? Delta x. So this delta x is nothing but the film thickness at location x. Do you all agree with me? Yes or no? Does it make sense to everyone what we are doing?
Yes, sir.
Your S is lacking that confidence. Is it clear?
Yes, sir. Yes, sir. It's clear.
Okay. So you are saying yes, sir. So that S is coming with some reservation. Okay. So that's why I'm asking again, is it really clear or not clear? If something is not clear, we will discuss again. Okay, all right. So now we have obtained the rate of condensation. Remember, in the last class itself, I said that what we are going to do? We are going to find out the rate of condensation from the velocity profile first. And then we are going to find out the rate of condensation from the heat transfer, because how much amount of vapor is condensing in this film, that depends on the heat transfer, isn't it? So if I find out the heat transfer, I can pinpointedly find out what is the rate of condensation at any x. Does it make sense to everyone? Isn't it? So what I'm trying to say here is, see, as I'm moving from this leading edge in a downward direction, thickness of my film is increasing because more and more amount of vapor is getting condensed as I'm moving down, isn't it? And therefore this film thickness is increasing. This film thickness is increasing. So if I'm looking at any location x here, any location x from the top, isn't it? I can say that the rate of condensation I can find out from the heat transfer, isn't it? So if I find out the heat transfer at any location x, that heat transfer itself is resulting into the increase in the thickness. Isn't that heat transfer itself is increasing in the condensation of the vapor, isn't it? So if I know the rate of heat transfer, I can divide that by a latent heat of vaporization. I can directly find out the rate of condensation. Do you all agree?
Yes, sir.
So we have first found out the rate of condensation from this velocity profile. We have found out the rate of condensation from this velocity profile. Now we are going to find out again the rate of condensation from heat transfer, and then we are going to equate. And then we are going to equate both, isn't it? That's what we are trying to do here. So what is our aim? In this entire exercise, what is our aim? Our aim is, can I quantify the thickness of this film as I move from this x, isn't it? That is what I'm trying to find out. And what will be the rate of heat transfer? What will be the heat transfer coefficient at any particular location? Or if I wanted to find out the average heat transfer coefficient, what will be that? These are the things which we are trying to find out from the first principle. Okay.
Average for the complete film or
average
just
for the complete film. Average for the complete film. So we will find out the local heat transfer coefficient. So that is dependent on the x. But then we will find out the overall heat transfer coefficient for the entire film. Isn't it? Because in a practical application, I am not interested in finding out what is happening at one end and the another end, isn't it? Rather, I am wanted to have a complete picture over the entire plate, isn't it? Entire surface, isn't it? So there I need a overall heat transfer coefficient rather than looking at the local heat transfer coefficient. Do you all agree with me? Does it make sense?
Yes, sir.
Okay. So far we have found out rate of condensation using the velocity profile. Now, as discussed in the slide itself, we said that the only resistance occurring in the condensation here is the conduction occurring between this wall and this vapor here, isn't it? So only conduction resistance is present here. That's what we are assuming, isn't it? So I can apply a Fourier law of heat conduction for this film, assuming that the film is stagnant, isn't it? So remember, Fourier law of heat conduction is only applicable when we are assuming that the film is stagnant. So that's an assumption. That's an assumption, isn't it? If there is some movement, definitely we should not look at the Fourier law of heat conduction. Rather than that, we have to include some other additional impact there, isn't it? Because bulk motion is there, isn't it? But in this case, the assumption we are taking is the film is stagnant. There is some movement, but since we are assuming that it's a laminar flow, so velocity is not very high. So with a reasonable accuracy, we can apply a Fourier law of heat conduction here for the entire film. So rate of heat transfer we can obtain by a Fourier law of heat conduction directly as KL into, this is the change in the temperature, isn't it? TV to TW, isn't it? So TV is the temperature of the vapor, minus TW is the temperature of the wall. So that is the delta T into thermal conductivity divided by the thickness of the film, that is delta at a particular X. So that gives me heat flux. That gives me heat flux at a location X from the top, isn't it? And this heat flux I can multiply to a area. I will get a rate of heat transfer. Do you all agree? And what will be the area for the heat transfer here? Area for the heat transfer will be, if I look at this particular element itself, dx into z, isn't it? Dx into z will be the cross sectional area. Do you all agree? Yes or no? Because the heat transfer is taking place in which direction? Heat transfer is taking place in this direction, isn't it? Heat transfer is taking place in this direction. Correct. So what will be the cross sectional area? Cross sectional area will be the cross sectional area across this particular plane, isn't it? So what that will be? Dx into dz. Do you all agree? Dx into z, sorry, because we are not assuming that variation in a z direction. Does it make sense to everyone?
Yes, sir.
So is my slides visible?
Yes, sir.
Okay, all right. So that's what we have done. We have found out the heat flux first by using Fourier law of heat conduction multiplied by area dx into z. Z is just 1, so that we have done here, isn't it? So we have obtained this equation. Now this particular equation divided by latent heat of vaporization. Latent heat of vaporization will give me rate of condensation, isn't it? Correct. If I divide this equation by LV, that gives me the rate of condensation, isn't it? That will give me the kg amount of vapor condensing per unit time, isn't it? Do you all agree? And since we are calculating it for the small element, that's why we have represented this as a dm. Is it clear? Does it make sense to everyone? I just divided this entire equation by LV. LV is nothing but latent heat of vaporization. So I got dm.
Yes,
correct? Sir. So from this equation, I can then find out dm by dx. Dm by dx is just this KL delta T divided by del LV, isn't it? That is what I'm going to get from equation.
dm is the mass of the film.
dm is nothing but the amount being condensed over the distance dx. because of heat transfer. It's not the mass of the film. No, it's not the mass of the film. It is the additional amount that will get condensed. That will get condensed over this particular surface. Isn't it because of heat transfer? Because mass here is also because of something which is carried from the previous thing, isn't it?
Yeah, yes, sir. Yes, sir.
Isn't it? So that additional mass added in this particular element is what dm. Does it make
Yes, sir,
sense?
yeah, the additional vapor condensed to liquid
Correct.
on the surface.
Correct. Yes. Okay. So again, this equation which we have obtained m, isn't it? I can differentiate this equation and I can get dm from this equation, isn't it? I can find out what will be the increase in the mass if I look at a particular location here in terms using this velocity, isn't it? So I can again find out dm. So I can differentiate this. So if I differentiate this, what I'm going to get, dm will be given as rho L into the bracket rho L minus rho V G divided by 3 mu L. So these are constant, but this delta is varying with respect to x. So this will be given as
3 del
3 del
squared
square d
eta.
del, isn't it? That's what we have obtained here, isn't it? After differentiating equation, rho L minus rho V G divided by 3 mu L, 3 del square d del, isn't it? And this we are equating to this. This we are equating to this, isn't it? dm. Correct. So after equating these two, after rearranging, what we get? We get this rho L minus rho V G del cube divided by rho L, because this del cube becomes because so this del is there on the right hand side also. So that goes on the left hand side. So this becomes del cube here. Is it clear to everyone? Hello?
Yes, sir.
Okay. And this 3 get cancel out. So okay. This 3 get cancel out with this 3. So just mu L is there. So ultimately what we get is we get rho L minus rho V divided by rho L into rho L minus rho V into G del cube divided by mu L d del, and on the right hand side we will get KL delta T divided by LV dx, and this equation we can integrate. So after integration of this equation, what information I'm going to get? After integration of this equation, I am going to find out what will be the thickness of the film at a particular x, isn't it? You can see as I move down here, as my distance x is increases, my thickness del is increasing. So I am finding out what will be my thickness at any x. What will be my thickness del x at any x from this equation? All agree? Does it make sense to everyone? Hello?
Yes, sir.
So after integration, what we get is this left hand side here is del cube d del is integrated over 0 to del, and the right hand side is integrated, dx is integrated over 0 to x, and all these constants are taken out from the integration. Okay, so after integration, what we get is rho L into the bracket rho L minus rho V G del raised to the power 4 divided by 4 mu L, and that should be equals to KL TV minus TW divided by LVX. And if we rearrange everything, what we get is del X is obtained as 4 mu L KL X TV minus TW divided by LV rho L minus rho V G raised to the power, this entire bracket raised to the power 1 by 4. So this equation gives me local film thickness. So thickness of my condensate film at any x. Remember, if I put x here, all other values are constants in a way, isn't it? TV is not changing, TW is a constant, LV, rho L, all these are the properties that you can find out. Only the x is varying here on the right hand side, isn't it? So if I put the value of x here, I can pinpointedly find out what will be the thickness of the film at that particular x. So del x is nothing but the local film thickness which we have obtained from this equation. Is it clear to everyone? Hello.
Yes, sir. Yes, sir.
Okay, so once we get this del x, now our aim was what? Our aim was to calculate the heat transfer coefficient. So heat transfer coefficient for the flat geometry of the film is what? KL by delta. That is what we have derived earlier, isn't it? KL by delta gives me the transfer coefficient, isn't it? So KL by delta, delta we have already found out from the previous equation. This is the equation. I can put it here. I get this another equation. LV rho L minus rho V G KL cube divided by 4 mu L X in the bracket TV minus TW, and this entire bracket raised to the power 1 by 4. That gives me the heat transfer coefficient. But this heat transfer coefficient is a local heat transfer coefficient. That everybody has to remember. This is Hx. This is Hx, isn't it? Because we have used this local film thickness in this equation, isn't it? So from this local heat transfer coefficient, I can again find out the local Nusselt number. So local Nusselt number will be given by Hx by KL. I can again multiply x by KL to this equation and I will get the local Nusselt number. So this local Nusselt number is obtained here. LV rho L minus rho V Gx cube divided by 4 mu L KL delta T raised to the power this entire bracket. Please go ahead.
The first equation contains d delta. I think that is wrong or something. Because what we have got doesn't contain d delta. Just the next step that is shown with the arrow.
You are saying this is wrong, you are saying?
Yes, sir. Where does d delta go in the next step?
There is no d delta. I think I have wrongly wrote that. There is no d delta here. You can see.
Yeah, there can't because we have integrated.
So this d delta is not there. This is not correct. I will thank you for pointing. This just cut paste from the previous equation, and because of that we missed the point. I will just correct it. Give me a minute. Format shape, fill, solid fill, white. Okay. Okay, all right. Thank you so much. Thank you so much for pointing. Okay, so there's no d delta because that is, see, we have already used that in the integration. So there's no d delta here. So that is just a mistake. Okay, so this local Nusselt number which we have obtained here, local Nusselt number we have obtained, isn't it? So this is the local, this is the Nusselt number at any x. But typically we are interested in the average values, isn't it? So what we have to do? So in order to get the average value, this local heat transfer coefficient, we have to integrate over the length. So 0 to L H dx by capital L, that gives me a average heat transfer coefficient. Do you all agree?
Yes, sir.
Isn't it? So this is just a straightforward integration. So we take this local heat transfer coefficient in the integration and integrate between 0 to L. Finally, what we get is this 4 by 3 L raised to the power 3 by 4 is here, and there is also 4 here inside this bracket raised to the power 1 by 4. So if you calculate the value, this 4 you take it out, what you get finally is 0.943 in, and in the bracket you get LV rho L in the bracket rho L minus rho V G KL cube divided by mu L delta T. And this entire bracket raised to the power 1 by 4. So if you look at the book, in the book there is one mistake. Okay, so in the book you can see that this 4 is also kept it here. So they have not eliminated that 4 here. Okay, so be careful using the expression. So that is this small mistake which is there in the book. Okay, so there is no 4 here. Is it clear? That 4 we have already taken out in this 943.943. Is it clear to everyone?
Yes, sir.
Okay,
Yes,
so
sir.
again, please go ahead. Some question was there from anyone? Hello? Okay, so no question is there. So then again, as I said that, remember in this equation, several properties are there, like latent heat of vaporization, rho L, mu L, thermal conductivity KL. These are the properties, isn't it? And all these properties has to be calculated at mean temperature. So what will be the mean temperature here? TB plus TW divided by 2. Okay, so that we have to remember. All right. So let's look at some of the correlations, some of the equations. So remember this equation we have derived for a vertical plate. This is for a vertical plate. So condensation occurring on a vertical plate. But let's say if you are having a horizontal plate, for a horizontal plate, single horizontal plate, the equation given is 0.728 LV rho L. So the only difference in this equation and this equation is, here instead of 0.943, the coefficient here is 0.728, and instead of capital L, there is a D, diameter of the horizontal tube. Okay, is it clear? And this is the condensation externally, outside, condensation outside. See here, condensation outside. So this is for a horizontal tube, laminar flow, and the diameter of the tube is D. Clear? But let's say instead of one horizontal tube, let's say we are having n horizontal tubes, and these are placed directly one another. So there are n tubes present in one column. In that case, so this n is what? This n is nothing but the n tubes are present in one stack. So let's say if there are 100 tubes, and how many stacks are there? Let's say there are 10 stacks are there. So what will be this n? What will be this n? If there are 100 tubes are there, and these are placed in 10 stacks, isn't it? There are 2 stacks I have shown here. What will be this n?
100 into 10.
No.
10.
That will be 10. Because
Tubes
each stack
will
will
be
have
10.
10 tubes.
Yeah, okay.
So this don't get confused with the wording here. What we are saying is n tubes placed directly over one another. So how many tubes will be there over one another? 10 tubes will be there if there are 100 tubes. Correct. So this n, don't use 100 here. Here will be a 10 into D. If you are using 10 tubes, one over each other, isn't it?
One stack would be counted like one.
Yes, one stack
like
will be
that.
counted one. So we will have, let's say 2 stacks are
Sir,
there.
so n is the number of stacks or the number of tubes in stack?
N will be the number of tubes present in each stack.
Okay, sir.
Okay. So that is the only difference. Again, here we will have a diameter, and this additional variable n is coming into a denominator here. So that you have to, take into the account. Again, the entire analysis which we have done for the film, if you derive everything for a sphere, you are going to get this 0.815, this entire equation, and in the denominator you will get D. Is it clear to everyone? Okay. So these 3 equations, please go ahead. These are not correlations. These are derived from first principle model. Okay.
So in this parallel stack equation, we are assuming the 2 stacks are independent of each other, right? So
2 stacks are independent of each other. Correct. Yes, absolutely. Absolutely. Yes.
Yeah, so calculation is done for each stack only.
Calculation is done for each stack. Yes. Precisely. Okay. All right. So these 3 equations are for condensation outside. But very often what happens is condensation is taking place inside the tube also, isn't it? So if you are using a single horizontal tube and inside that the condensation is occurring, then the equation has to be used in this. So the only difference here is this coefficient here is 0.555, and this, instead of taking the latent heat of vaporization, exactly here the latent heat of vaporization is calculated like this: LV plus 3/8 CPL TB minus TW. So we are also assuming that there is a so we are assuming the vapor is not saturated. So there is a temperature change in the vapor taking place. That's why this CPL into delta T we have used. CPL into delta T will give me the sensible heat, isn't it? So this sensible heat and this latent heat of vaporization both are combined into give a modified latent heat of vaporization, and that modified latent heat of vaporization is used in this equation. Is it clear to everyone?
Sir, how could condensation take place inside when the
So
when the
vapor
temperature difference
is okay. Vapor is flowing through a tube, let's say metal tube, and this metal tube may exchange heat with the ambient. So over the period, what will happen? The vapor inside the tube will condense. That's what happens, the condensation of the steam.
Whereas in outside case, what will happen? Like
So outside
be-
part we are not accounting here. This is nothing but the heat transfer coefficient for the inside heat transfer. So remember, the temperature of the wall is going to decrease, isn't it? As you more and more heat exchange is taking place with the ambient. So eventually what will happen to the steam? Initially it might be in a vapor state, but eventually it is condensing. So this equation is regularly used in the industry, because that's what you see. Most of the industry uses the steam, and you will see that the steam get condensed, isn't it? So to account that, you need to use this equation.
sir, and what happens in the condensation outside case then?
Outside case is this. Outside case. Okay, so outside heat transfer you are saying?
Yes, sir.
Outside heat transfer you can calculate using the forced convection or a natural convection, isn't it? Because that is the heat transfer occurring between the hot surface of the pipe and the ambient, isn't it? Okay, maybe I'll just explain. Maybe I think what confusion is, I understood. So let's say this is the tube. This is the tube. So in a real life application, what you will have, this steam tube or steam pipe will have the insulation here, isn't it? Correct. Now what phenomena we are talking about? The vapor is flowing, vapor or steam is flowing here. So what is happening here is, even though we have insulation here, but some heat exchange is going to take place from this surface here to the ambient, and because of that, this surface temperature TW is going to decrease, isn't it? So eventually this steam is going to condense in the form of droplets here inside. Now how you can account this entire phenomena? So you need to calculate the heat transfer coefficient here. You need to calculate heat transfer coefficient here. And also you need to calculate the resistance here, isn't it? So that will be the conduction resistance. So heat transfer coefficient here, HI, can be calculated using this equation. Heat transfer coefficient outside here you can calculate based on the natural convection or a forced convection, depending on what type of situation you are looking at, isn't it? And the resistance here will be what? The resistance here will be given by conduction. And then we are having the equation like 1 by Ui or 1 by U naught. Remember overall heat transfer coefficient, that we have to calculate based on this. Is it clear?
Yes, sir. Yes, sir. Now it's clear.
Now you got the complete picture what I'm trying to say?
Yeah,
Okay.
exactly. This was I was expecting.
All right. So these are the correlations we have to use. So this is all about the condensation and boiling. So we will move to the next topic, and next topic is radiation. Okay. So let me unshare unless you have any question till this point. Do you have any question till this point? Hello. So if not, if there's no question on this topic, let me unshare this and share the next topic, which is on radiation. Is my slides visible to everyone? Is my slides visible to everyone?
Yes, sir. Visible.
Okay, all right. So if you look at our journey in this course, how we started. The first class we have given the overview of all the heat transfer, phenomena. We have given some, description on conduction, convection, and radiation, not in detail, just to appreciate the concept. And then we have started with the conduction. We have looked at conduction. We have looked at multi-dimensional conduction, unsteady state conduction, variable area, everything we have looked at. From conduction, then we have moved to the concept of heat transfer coefficient. From concept of heat transfer coefficient, we have moved to forced convection. Then, sorry, just a minute. Just a minute. Okay, sorry for this interruption. So some insect was moving here and there. Okay, all right. Okay, so what I was saying is we started with the conduction. Then we have looked at the concept of heat transfer coefficient. Then we looked at the concept of forced convection, natural convection, then move to this condensation and boiling. Okay. Now we wanted to again go one step further. We wanted to look at radiation in detail so that this entire story completes. Remember, isn't it? So all three modes of heat transfer once we cover, the next topic is only the heat transfer equipments. So once we complete the radiation, we will look at heat transfer equipments and then the entire story completes. Okay. So let's look at the radiation in detail. So far we have looked at conduction and convection. So conduction and convection occurs when there is a temperature difference between 2 points in the medium. Isn't it? Whenever there is a temperature difference between 2 points in the medium, heat is transferred from one point to the another point. Isn't it? That's what happens in the conduction and convection. In conduction, there is no movement of the medium. In convection, even the movement of the medium is also there. Isn't it? But unlike this, if you look at the radiation heat transfer does not require temperature difference and it does not require even medium. Okay, so radiation heat transfer does not require these two things. Temperature difference is also not required and the medium is also not required. So eventually in the radiation we calculate what? We don't calculate the heat transfer, we calculate the net heat transfer between the bodies. Net, this word net is very important. Why I am stressing on this word net is because if you look at this particular example, see, this particular body A is having the temperature, let's say 500 degrees Celsius. There is another body which is having the temperature of 100 degrees Celsius. So both body A and both body B, both are transferring heat to each other. Body A is transferring heat by radiation. Body B is also transferring heat by radiation. But eventually what we look at the net difference between these. So body A is transferring more heat compared to body B, and therefore the amount of heat received by body B is more than what it is transferring. So you are calculating the net rate of heat transfer, the difference between the rate of heat transfer between these two bodies. That's what we calculate. So that is why I said the heat transfer does not require the temperature difference, because this body is transferring heat to body A, irrespective of whether the body A is at a higher temperature. Even though this body would have been at 100 degrees Celsius, still there would have been the heat transfer between these two bodies. Of course, there will not be a net heat transfer, but heat transfer would have been there, isn't it? Do you all agree? Does it make sense what I'm trying to say? I am saying heat transfer will be there. If both these bodies are, let's say, at 100 degrees Celsius, there will be a heat transfer between both the bodies, but net heat transfer will be 0. Does it make sense to everyone? Hello?
Sir,
Please go ahead.
Can you repeat how the net heat transfer would be 0?
So net heat transfer, okay, so see amount of heat, if both these bodies are at, let's say at 100 degrees Celsius, whatever the amount is radiated from this body A is same as the amount of heat gained by body A, because both these bodies are there, isn't
Yes,
it?
sir. Yes,
So
sir.
in that case, what will be the difference?
In that
Zero,
case, it
isn't
would
it?
be
So
0.
net heat transfer is 0. Okay.
Yes, sir.
Okay, so that's why these words are, carefully used here. Heat transfer does not need a temperature difference. Also, we don't require a medium here because the heat transfer taking place in terms of what? Electromagnetic waves, isn't it? So you don't require a medium for transfer of these electromagnetic waves. And therefore, both temperature difference and medium is not required for the radiation. All right. Why radiation is important? Because if you look at very large number of process applications like combustion of fossil fuels, operation of furnaces or thermal cracking, in such cases the temperature is considerably higher than the ambient temperature. So in such cases you will not be able to neglect the effect of radiation. Remember, very often when we do the calculation for conduction and convection, we assume that the temperature is not very high, and because of that we are not considering the impact of radiation. But as the temperature goes above the ambient temperature, it becomes significant, isn't it? Correct. So in such cases, the radiation effect of the radiation, impact of the radiation is also included. So that's what is written in the next line. Radiation becomes significant when the temperature is considerably different from that of ambient. Again, the radiation heat transfer is primarily takes place by emitting the electromagnetic waves, and bodies emit the electromagnetic waves at all temperature except absolute zero. So except absolute zero, at all temperatures radiation is there. Whether we account or not, that is a different question. But radiation will always be there at all temperature except absolute zero temperature. Again, these electromagnetic waves are moving with the speed of light. So if you look at the emission of radiation occurs from the surface or a body, and these waves propagate with the speed of light. And what is the speed of light? 2.998 into 10 raised to power 8 meter per second. So speed of light is denoted by this variable C. Okay. Again, the radiation of an electromagnetic waves is characterized by wavelength lambda or its frequency. Okay, so all these electromagnetic waves are characterized using wavelength lambda and frequency. And how these are related? These are related by this equation. So C is given as nu lambda. So nu is nothing but the frequency and lambda is the wavelength. So frequency into wavelength gives me the speed of light, C. Okay, that's how it is related. Further, the emission of the radiation is not continuous. Emission of the radiation is not continuous. In fact, the radiation takes place in a discrete quantas, isn't it? So the radiations are emitted in terms of discrete quantas, and the energy of each of these quanta is given by h nu, where h is a Planck's constant. So from this equation, one can clearly see that the energy of a particular wave is inversely proportional to the wavelength. So if I replace this nu here by C by lambda, remember C is constant. So what we can say? We can say that the energy emitted in each quanta is inversely proportional to wavelength. Okay, so that means what? A shorter wavelength waves are going to give you more energy compared to the large wavelength waves. A typical example is if you look at X-ray or cosmic rays, these are having the shorter wavelength, gamma rays, etc. And therefore the energy present in those waves is much higher compared to compared to the ultrasound waves, isn't it? Ultrasound waves will have a very low wavelength. Is it clear to everyone? Very high wavelength, sorry. Is it clear to everyone? Another interesting thing to note down, when we are saying that the energies are emitted in terms of discrete quantas, so how the energy emitted? If you look at a molecular or an atomic scale, when the electrons are moving from one state to the next state, from ground state to the excited state, it absorbs the quanta. And when it comes from excited state to a ground state, it emits the quanta. And that's what results into the radiation, isn't it? That's what results into the radiation. That is what is written. Oscillation or a transition of electron basically lead to the emission of the electromagnetic waves. Is it clear to everyone whatever we have said? In fact, this entire detail you probably would have done in much more detail in your JEE days. So this is just a recap of what we have already done earlier. Is it clear to everyone?
Yes, sir.
Okay. So this is what I was saying. So as the wavelength, as I said, the energy is inversely proportional to wavelength. So here you can see that typically, if you look at the body typically emits the wavelength at all wavelengths, isn't it? Body emits the radiation at all wavelength from 0 to infinity, isn't it? So, but what is the significant fraction is present in which particular wavelength, that decides the energy. For instance, in this case, you can see, so visible light. In the visible light has the wavelength between 0.4 to 0.7 micrometer. So this is the very short width which comprises of visible light. So this is between 0.4 to 0.7 micrometer. And so if you look at the sun is emitting lights from 0 to infinity wavelength. It is emitting all wavelength light. But the majority of the fraction is lying only in this short band between 0.4 to 0.7. And that is why sun appears bright to us. That is the reason why sun is visible to us. That's why we are calling it as a visible light. Okay, because almost if you calculate, or we will see that calculation in the subsequent slide also, you will see that almost 36% of the sun's radiation primarily present only in this short width between 0.4 to 0.7, and that's why sun appears bright to us. But if you look at the
there is
okay,
shift of the color as well.
Yes.
It is white and see a little more yellow.
So this entire, if you look at this violet to red, this entire thing basically comprises the white, isn't it? You can individually divide this into violet all the way to red.
Yes,
that's what you see when you put a prism and pass the light through it. It splits into 7 colors, isn't it?
Yes, sir.
So that basically gives the spectrum here in this region. Does it make sense?
Yes, sir.
Okay, but the more important point I wanted to say here is sun is not radiating the energy only in this spectrum, in this region, small region. It is emitting from 0 to infinity. It is emitting between 0 to infinity. But only this part we are able to see. Why? Because the majority of the radiation coming from the sun is falling into this range. That's why the sun is appearing bright to us. But if you consider the other emissions, like other radiations like cosmic rays or X-rays or even microwave or ultrasound waves, you are not able to see them. You are not able to see them because their wavelength is not in a visible range. You are not able to see them, but sun you are able to see because majority of that radiation is falling in this visible range. That's why you are able to see sun and not all these rays. Another important thing to note down is, as you are moving towards left, that means you are moving towards the lower value of wavelength, the higher energy you are going to have. So cosmic rays, X-rays, gamma rays, these are going to have really very high energy, isn't it? But if you consider the right hand side here, so here you can see the wavelengths are very high. So here the energy of ultrasonic waves or microwaves, these are lower as compared to this. Is it clear to everyone? Does it make sense to everyone? Remember, that's what we have said here. See, if we put here, if this nu I replaced by C by lambda, I can clearly see that the energy is inversely proportional to the wavelength, isn't it? Make sense to everyone? In fact, this you would have done in much more detail in your preparation, JEE preparation, I guess.
Yes.
Okay, all right. So just for the continuity, I am doing it again. Please forgive me if it is a repetition. All right. So the next point is, okay. So when incident radiation is, if the radiation is incident on a body, what happens? There are three things happens, isn't it? One is the radiation is absorbed. Second is the radiation is reflected. And the third one is radiation is emitted. So when the radiation is incident on a particular body and it is absorbed in the body, its temperature increases. Isn't it? And depending on the nature of the body, whether the body is opaque, whether the body is polished or permeable, how much amount of that is going to get absorbed, reflected or transmitted, it depends on that. So if I'm having a perfectly opaque body, in that case, all the incident radiations will be absorbed. If I'm having a body which is polished, in that case, all the radiations will be reflected. If I'm having the body which is the permeable like a glass, in that case, all the incident radiations will be transmitted through it, isn't it? Also, in terms of the reflection, there are two types of reflections are there. When the angle of incident and angle of incidence is same as angle of reflection, in that case, the reflection is called as a specular reflection as shown here. So both these angles are same. But there is another type of reflection is also there. So this is called as a diffuse reflection. So the incident radiations are reflected in all directions. This is called as a diffuse reflection. Again, there are three quantities which are used to represent each of these phenomena. So the fraction of the incident radiation which are absorbed are represented using absorptivity. The fraction of the incident radiation reflected are represented using reflectivity, and the fraction of incident radiation which are transmitted through the body are reflected through transmissivity. Okay, and the summation of absorptivity, reflectivity and transmissivity is equals to 1. So transmissivity is denoted by tau, reflectivity is denoted by rho, and absorptivity is denoted by alpha. So tau plus rho plus alpha is equals to 1. Another interesting concept is emissivity. Okay, or emission. Don't get confused with emission and reflection. They are not same. Reflection is what? Whatever the incident radiation is, the radiation coming on the surface, it is getting reflected. That is called as a reflection. But what is emission? The radiation is absorbed in the surface, and this after the absorption of the radiation, the temperature of the body is increasing, and because of that, the energy is now emitted from the surface. So reflection and emission both are different. Okay. Another interesting thing to note down here is emissivity. Emissivity is basically nothing but the measure of how good a particular surface is as an emitter. Okay. So in general, a black body is used as a basis to quantify all these things. Okay. So that we will see in the subsequent slide. Is it clear to everyone what we are saying so far? Does it make sense? Hello?
Yes, sir.
So that S is again not having the confidence. Is it?
No, sir. It is like already we are aware of.
You are already aware. Okay. So that is a good thing to hear from you. Okay. So let's move then. Even this concept of black body also you might have done, but just for a sake of continuity, I will cover so that some more complicated things we will see subsequently. Okay. But just to have the basis clear to everyone, we will cover this. Okay. So black body again. Black body is the basis used for comparing the other bodies. Okay. So what is black body? Black body is the surface which completely absorbs the incident radiation. Okay. So at all wavelengths. So you can see any radiation falling on the surface are absorbed completely inside. It's not escaping from the body. So since all the radiations are absorbed by the body, there is no reflection and therefore this body appears black. Okay, therefore this body appears black. Again, black body is a perfect emitter. Perfect emitter in the sense we are saying the emissivity of the black body is 1. So that is what the basis we take, and compared to with that basis we compare all other real bodies. So emissivity of the black body is 1. So again, one more important thing is since emissivity of the black body is 1, and if you look at the other real surfaces, their emissivity will be lower. So what it means? It means that the black body will always emit more than the normal surfaces at any given temperature. Again, the black body is a perfectly diffuse emitter. That means it is going to emit the radiation in all directions. It is not going to emit in one direction. As we said, the black body is a perfect emitter as well as absorber. Its absorptivity, if you see, absorptivity is also 1. Okay. So as I said, it is used as a standard to compare the real bodies. Okay. So real surface. Now let's look at the real surface. So real surfaces emit or absorb less than the black body. So that means their absorptivity and their emissivity is always less than 1. Also, the emissivity and absorptivity of the real surfaces depends on temperature and wavelength. Absorptivity and emissivity we are seeing. For black body, these are independent of temperature and wavelength. For a black body, emissivity and absorptivity both are equals to 1, and these are independent of temperature and wavelength. But unlike that, real surfaces, you will see that the absorptivity and emissivity are dependent on temperature and wavelength. Now there is another body which is in between real and the black body, and this body is called as a gray body. Now gray body has emissivity and absorptivity less than unity like a real surfaces, but these are independent of wavelength like a black body, and that's why we are calling it as a gray body. This word gray we are using because it is in between real and black body. Is it clear to everyone?
Sir, for gray bodies, is it true that emissivity and absorptivity are equal?
You are saying for a gray body, the emissivity and absorptivity are
Equal, like yes, less than 1 and they both are equal.
Less than 1 is true, but equal in general, that is governed by this Kirchhoff's law. Remember, when these are in a thermal equilibrium, then these are equal, isn't it? That's what the Kirchhoff's law says, isn't it?
Okay, sir.
In a thermal equilibrium, yes, but otherwise not sure. That anyway we will look at in the Kirchhoff's law, that absorptivity and the emissivity of this real surfaces or even gray surfaces when these are thermal equilibrium with the surrounding is equal. That is what we are going to see. Okay. All right. Okay. So next thing is a Planck's law. So Planck's law, the statement of the Planck's law is monochromatic emissive power of a or a spectral emissive power, which is denoted by EB lambda. So we are talking about the monochromatic emissive power or a spectral emissive power of a black body. So these two subscript B and lambda denotes what? The first subscript B denotes a black body, and the second subscript lambda denotes that this entire quantity we are looking at only one wavelength. That's why we are calling it as a monochromatic. So monochromatic emissive power or a spectral emissive power EB lambda of a black body is a function of wavelength of the radiation. That is what the Planck's law. And this relationship is given by this equation. EB lambda is given as 2 pi hc square lambda raised to the power -5 divided by exponential of hc divided by lambda kBt minus 1. So in this entire equation, h is a Planck's constant, c is a speed of light, kb is a Boltzmann constant. So you can rearrange all these constants together. So by rearranging these two constants, we are putting these two constants k1 and k2 in numerator and denominator. So k1 we can calculate as 1.4387 into 10 raised to power -4 micrometer Kelvin, whereas k2, whereas k1 is given as 3.743 into 10 raised to power 8 watt micrometer raised to the power 4 by meter square. So first is k2 and second one is k1. So this we can directly calculate by putting this speed of light, Planck's constant, Boltzmann constant, and value of pi, etc. in this equation. Okay. So this is a very interesting law. This law says spectral or monochromatic emissive power of a black body depends on the wavelength. Depends on the wavelength. That's what it says. Okay. Now, if you are looking at the real surfaces or even a black body, you can say at any given temperature, this black body is going to emit the radiation in all wavelengths from 0 to infinity, isn't it? Correct. As I said in the previous slide also, I said the bodies are going to emit the radiation in all wavelengths from 0 to infinity, isn't it? But most of these radiation are concentrating in which range that defines the energy, or that defines the energy, or even sometimes the color of the object. Okay. So now in this case, what we are saying is we are not talking about all wavelength. We are only talking about one wavelength, and that's why we are calling it as a monochromatic or a spectral. So monochromatic emissive power or a spectral emissive power depends on that particular wavelength. That's what this particular law is saying. Okay. A typical example is sun. If you look at the sun, the temperature of the sun is 5800 Kelvin. It emits the radiation with a peak near visible range. Why peak near visible range? Because most of the radiations are concentrated in that range. Even though sun is emitting the radiation in all wavelengths, but since most of the radiation, almost 36% of the radiations are present in that visible range, and that's why sun appears bright to us. But if you consider Earth is also emitting radiation in all wavelength, 0 to infinity. But most of the radiations coming from the Earth are in infrared region, and that's why we are not able to see the radiation from the Earth. Okay. So Earth is not appearing bright to us because of that. Okay, so what we were saying here is the same concept is here. You can see that as the temperature increases, the power of those radiation is also going to increase, isn't it? The energy in those radiation is also going to increase. So what does that mean? That means that the majority of these radiations will be focused towards the lower value of the lower value of the wavelength, isn't it? So that's what is happening here. You can see if my body is having the temperature 50 C, it is also going to emit all the radiations. It is also going to emit all the radiations, but its majority will be focused at almost 70 or 80 micrometer. But if you consider a sun here, sun is having the temperature of 5800 Kelvin, isn't it? So you can see most of the radiations are concentrated between 0.4 to 0.7. You can see here, isn't it? If I consider, let's say, gamma ray or a cosmic ray, I will get a higher peak here somewhere. So you can see that the peak of these individual, the distribution of the wavelengths, this peak of this individual distribution of the wavelength is shifting towards the left hand side as the temperature increases. Isn't it? So that's what is written. Radiation are concentrated towards the peak lambda max, and this peak is going to shift towards the left as the temperature of the body increases. Do you all agree with me?
Yes,
Hello?
sir, I have a question.
Please go ahead.
Sir, let's consider a black body and it radiates. Its emissivity is 1 and absorptivity is also 1. So in that case, like whatever it absorbs, it will emit out.
Yes.
Is it like that?
Yes. That's what it is. So black body, whatever, so its absorptivity is same and its emissivity is also same, isn't it? 1. Correct.
Yes,
so whatever it is absorbing, the same it is emitting, isn't it?
Also, sir, if there is a body that is reflecting as well as emitting, so the wavelength, which is the peak wavelength, will be the one which has to be decided, which has, like, it can be either of
reflection. So see, in this particular figure, we are not talking about the reflection or the transmission. Why? Because this entire figure is for a black body. You can see this is for a black body.
Reflective is 0.
So reflectivity and transmissivity is 0 here. We are only talking about the black body. In fact, if you look at the distribution for a real body, that will be lower than this. So this curve I have shown for an individual one thing. For a same temperature, the curve obtained for the gray body or a real body will be lower. So you will typically get a curve like this. Let me just draw it by a different color. So for a real body, for a same 5800 temperature, for a gray body, you will get a curve like this. Sorry, I have not drawn it properly, but proper curve will be there. But for a real body, this will be for a gray body. For a real body, you can have a variation like this. Instead of having a very well, unimodal curve, you can have even a multi-modal curve for a real bodies. Is it clear? If that is what the question is.
Yeah, exactly. That was I was referring to.
So it will be lower than this curve. Okay. So Planck's law, as we said, the monochromal or a spectral emissive power of a black body is a function of wavelength of the radiation. That is what the Planck's law. Now, the next law is a Wien's displacement law. This is a very interesting law. What this law is saying is, if I look at the wavelength corresponding to each of these maxima, and multiply that to a corresponding temperature.
Sir.
Hello. Yes, please.
Sir, your slides are not visible. I mean, just now.
Just now. Okay. Thank you. Let me just share it again. Sorry. Okay. So what we were saying is, here we have talked about the Planck's law, where we said that the monochromal or spectral emissive power of a black body is function of a wavelength of the radiation. That is what we said. There is another law which is a Wien's displacement law, and this law is very interesting law. Why I'm saying interesting? Because this law says if you multiply the wavelength corresponding to each of these maxima to its temperature, then it is constant. So lambda max is nothing but the wavelength corresponding to each of these maxima multiplied by corresponding temperature. This multiplication is constant for all these, curves. So lambda max into T is constant, and that is equals to 2898 micrometer per Kelvin. So at the peak of this plot, spectral emissive power versus lambda of a black body, if you calculate lambda max into T, that is equals to a constant value 2898 micrometer Kelvin. This is the Weiss displacement law. This particular law we can prove directly. Okay. So you can see that the spectral emissive power for a black body is given by this equation, isn't it? 2 pi hc square lambda raised to the power minus 5 exponential of divided by exponential of hc lambda kbt minus 1. This equation we can represent in terms of k1 and k2. So simplified equation is k1 lambda raised to the power minus 5 divided by exponential of k2 divided by lambda t minus 1. Now what we are interested in? We are interested in finding this lambda value corresponding to the maxima, isn't it? Maxima of each of these curve. So what we have to do? For maxima, we have to differentiate this equation with respect to lambda and equate to 0, isn't it? That will give me. So that's what we have done. This equation we have, differentiated with respect to lambda and we have equated to 0. So after equating to 0, what we get is k2 by lambda t equals to 4.965. So this gives me the lambda value corresponding to the maxima. So lambda max into t comes out to be k2 divided by 4965, and k2 we already know 1.4387. That's what we have, calculated here also, isn't it? K2 is just putting this constants. We got this k2 value. So if you put the value of k2 and calculate it, what you get is lambda max into t comes out to be 2898 micrometer Kelvin. Is it clear to everyone? Is it clear to everyone?
Yes, sir.
So another common example to appreciate this concept is this. So if many of you might have seen, if you hit the metal, initially the metal appears, red, then it appears yellow as the temperature increases. And if you further increase the temperature, it appears white, isn't it? So basically what color you are able to see? You are able to see the color corresponding to, most of the time you are able to see the color corresponding to this maxima. So whatever is the wavelength you are having with respect to this maxima, remember most of the radiations will be concentrated towards this maxima because you are having this Gaussian type of curve, isn't it? So you will have a tail here, you will have a tail on the left hand side, but most of your radiations will be concentrated towards this maximum value, isn't it? So
but sir, that is not a black body metal.
That is not a black body matter. Correct. So but even for a real body also you will.
Wien's displacement law is valid for only black bodies, or true for metals also, like
This
real
is for a black body. These are for a black body, but real bodies, see how we are, calculating things for real bodies.
It's a little bit deviation. It is a little bit deviation from the black body, like that.
So we calculate for black body first, and then we either multiply absorptivity or emissivity to calculate it for a real body. That's what we do, isn't it? Isn't it?
Okay, sir. Yes, sir.
So we are doing all these bases we are deriving in terms of black body first. But whenever we wanted to calculate something for a real body, either we assume that as a black body, that is the first thing, or we calculate the real values for the real bodies by multiplying its absorptivity or emissivity, depending on what we are calculating, isn't it? Also, in addition to that, some other factors come into the picture, like shape factors. What is the shape factor? What is the shape factor or a view factor? Those things we are also going to see in much more detail as we progress. Probably those things you have not seen. Probably you might not have worked around those things in your JEE days. So those complications will come eventually. But right now we are doing the same thing.
Effective surface area one, like that.
Please
The
go ahead.
effective surface area like that.
Yes, effective surface area.
Like
That
for a
you have done?
sphere, it will be a disk. For a sphere, it will be a disk.
Correct, correct. So how you are viewing a particular surface from the distance, that solid angle defines the view factor.
Yeah, yeah, yes, sir, yes, sir.
So those concepts, and in fact more than that, we are going to see eventually. So right now we are concentrating on a black body, but eventually you will see that we will slowly digress to the real bodies. Okay, that's what we actually see, isn't it? Does it make sense?
Yes, sir.
So if your question is whether we are going to see all these concepts for real body or not, yes, we are going to look at. Some more complications are going to come in, and that we will do it as we progress. So maybe in the next class or next to next class, you will get to know. Is it clear? If that is what the question is.
Yes, sir.
All right. What is the time? It is already time. Okay, I will do one more slide and then we will stop. So there is another interesting law. So we started with the Planck's law. We move to the Wayne's displacement law, and now we are looking at Stefan Boltzmann law. So unlike the Planck's law or even a Wayne's displacement law, these were concentrating mostly on what? These were concentrating on monochromatic emissive power. That means we are looking at the radiation corresponding to a single wavelength, a fixed wavelength. But in a real life, do you get that type of radiation? You get a radiation which are having the wavelengths varying from 0 to infinity, isn't it? Yes or no? Isn't it?
Yes, yes.
As I said in the previous example of this sun, I said that sun also emits the radiation. You can see here, you can see in this curve, if you look at, it is emitting the radiation in all wavelength, but majority are focused in this. The majority are focused in this area. Majority are focused area in this area, but actually it is emitting from 0 to infinity, isn't it? It is emitting from 0. This entire curve is from between 0 to infinity. So the point which I am trying to make here is Planck's law and Wayne's displacement law. These are only looking at the monochromatic emissive power or a spectral emissive power. They are not looking at the complete distribution. They are not looking at the complete distribution. So that is where, is my slides visible to everyone? Hello? Is it visible?
Yes, sir.
Yes, sir.
So that is where this Stefan Boltzmann law comes into the picture, because it talks about the radiation over all the wavelengths from 0 to infinity. Can you see the point why Stefan Boltzmann law we are looking at? So Stefan Boltzmann law states that the emissive power of a black body over the entire spectrum of the wavelength EB can be obtained by integrating EB lambda over lambda. So here you can see we have denoted EB. When we are saying the total emissive power of a black body, there we have omitted this subscript lambda, isn't it? So EB is nothing but the emissive power of a black body. Earlier we have represented this as EB lambda, so that lambda we have omitted because we are now considering all the radiations from 0 to infinite wavelength, isn't it? How we can obtain? We can directly obtain by integrating EB lambda over lambda, isn't it? So we get EB as integration between 0 to infinity EB lambda d lambda. Is it clear to everyone? Please go
Sir,
ahead.
this integral of 0 to infinity EB lambda into d lambda, it is true for black body only to give
We are
the
talking about the black
emissivity.
body only. See, that's why the subscript we have written B.
Oh, okay, okay.
That's why we have written the subscript B, isn't it? So this is over the black body only, because this EB lambda expression which we have put it here is corresponding to black body, isn't it? Planck's law is only for a black body. Got the point?
No, sir, I wanted to know that you showed that there will be curve for real surfaces and gray body too.
Those will be lower
For
than
them,
that, but those curves
yeah,
we are not talking about here. We will come back to that. We will come back to
but
that.
integral of that whole area will give their emissivity? I am asking that.
Integral of that curve, okay, but okay, so you are saying that E lambda integrated over 0 to infinity d lambda will give me a capital E or not? That is what the question is. Yes, that is true for everything, isn't it? If you know how your E lambda is varying, E lambda is nothing but what? Monochromal emissivity, monochromal emissive power of a real body. That's what you are saying? Okay.
Yes, sir.
So
Yes, sir.
this integral gives me what? This integral gives me a cumulative value over the entire wavelength. That you can get it for anything, isn't it? Even for a gray body. The only problem here, gray body or real body also you can get it. But the only problem is EB lambda, which we are getting the expression here from Planck's law. Such expression you cannot write for a real body.
Yes, yes, that I got it.
Okay, all right. So now here, this is the integration between 0 to infinity EB lambda d lambda. This expression of EB lambda, we have put it directly from the Planck's law. Again, as we said, so this equation we can rearrange little bit. So this expression is represented slightly different way. So we have taken this K1 common and we have multiplied this by t raised to the power 4 divided by K2 raised to the power 4. So this additional multiplication of t and division of k are adjusted here. So K2 divided by lambda t we have done. So you can see that this lambda raised to the power minus 5 is there. So lambda raised to the power minus 3 is compensated here. But additional lambda square is compensated somewhere else here. Okay. So this lambda 1 by lambda square and here 1 by lambda cube. This total becomes lambda raised to the power minus 5. Is it clear? This lambda is compensated here. Correct? And K2 and T, these are compensated with this T raised to the power 4 and K2 raised to the power 4. Why we have done this specific rearrangement is, with this specific rearrangement, now we can put K2 by lambda T, this K2 by lambda T by another variable X. So our integration becomes easy, isn't it? That's why we have rearranged this. So after rearranging, now we can put K2 by lambda T as X. So if we differentiate this, dx will be what? Dx will be minus K2 divided by lambda square T d lambda.
The last term.
Yes, isn't it? So now this entire last term we can represent as a dx. Isn't it? So with this, again, at lambda equals to 0, this is the initial value here, isn't it? And final value is infinity. So at lambda equals to 0, x is infinity, because if you put lambda here 0, you will get infinity as x. When lambda is infinity, then you get x equals to 0. So limits are going to change from infinity to 0, isn't it? But there is a minus sign here. This minus sign is there. So you can still rearrange it from 0 to infinity. Is it okay? By eliminating this minus sign. Make sense?
Yes, sir.
So that's why this entire equation after putting x becomes this. K1 t raised to the power 4, K2 raised to the power 4, integral 0 to infinity. That minus sign we have, was there here. This minus sign was there. So that minus sign we have adjusted by changing the limit from infinity to 0 to infinity. Okay. Here in the numerator, K2 divided by lambda t cube is there. So that becomes x cube. In the denominator, what we will have? Exponential of K2 by lambda t is there. So that will become e raised to the power x minus 1. So e raised to the power x minus 1, I can take e raised to the power x common. So that becomes 1 minus e raised to the power minus x. And outside I will have dx. Is it clear? This makes sense? This everything is clear? Up to this? Yes or no?
Yes, sir.
So then just now this e raised to the power x 1 minus e raised to the power x, I can take it in the numerator, that becomes e raised to the power minus x, and 1 upon 1 minus e raised to x. This I can represent using the Taylor series expansion. So this Taylor series expansion of that term is given by this. Again, I can multiply this e raised to the power minus x to this entire term. I get e raised to the power minus x, e raised to the power minus 2x, and that summation goes all the way to e raised to the power minus nx. So I can represent this only this integral as summation of n equals to 1 to infinity integral 0 to infinity x cube e raised to the power minus nx dx. Okay, now this nx term I can represent by another variable, let's say y, and if I rearrange, what I get is nx equals to y. If I put it, so n into dx will be what? Dy. So that means dx will be what? Dy by n, isn't it? Correct. So if I put it that here, what we get is 1 by n4, we will get it out, and integral 0 to infinity y cube e raised to the power minus y dy. Now this particular integral is a gamma function, and the integral of the gamma function, that if you look at the mathematical book, that comes out to be the factorial here, 3 factorial precisely in this case. So you will get the integral of this gamma function as 3 factorial. So after integration, what you are going to get is summation 1 by n raised to the power 4 3 factorial. And if you do this summation will be what? 6 summation 6 by n raised to the power 4 1 to infinity. And this summation comes out to be pi raised to the power 4 divided by 15. This is something called as Euler's identity or something. If you look at mathematical book, this is something called as Euler's theorem or something. Okay, so this summation comes out to be pi raised to the power 4 by 15. So if you put this integral as a pi raised to the power 4 by 15 in this particular equation, remember this integral only we have looked at. If you put it here, K1, K2, everything you know, pi you know, this 15 also you know. So this all these constants are collected together, and these constants are represented by sigma, and this sigma is nothing but Stefan Boltzmann constant. So this Stefan Boltzmann constant comes out to be 5.669 into 10 raised to power minus 8. So this entire analysis gives me what? This entire analysis gives me total emissive power of the black body is sigma multiplied by temperature raised to the power 4. So that is what the Stefan Boltzmann law is, isn't it? So emissive power of a black body is proportional to the 4th power of the temperature. That is what the Stefan Boltzmann law is. Is it clear to everyone? Does
Yes,
it make
sir.
sense? Okay, so we will stop here and we will continue from this point onward. So I have one more request. So can we have a class on Sunday morning? Extra class, 9:30.
So when did you say? When?
Sunday.
13th.
Sunday morning we will have 9:30 to same class, same time.
So there is a class on Saturday, I guess.
Which Saturday?
This Saturday.
So this
Is it-
Saturday we will not have. Instead we will have on Sunday. Is it okay?
Okay, sir.
Can we have it on Sunday?
Okay, sir.
9:30 to 11:30. Okay. So let's stop here. We will continue on Sunday. Okay.